So I'm going to tell you about the types of the complexes. In the types of the complexes, first coordination compounds or the complex compounds are one and the same. In the coordination compounds, there are different types. One is the cationic complexes, the second one is the anionic complexes, and the third one is the neutral complexes. In the cationic complexes are the complexes which carries the net positive charge. They have a positive charge on their square parenthesis. On the square brackets, you can see the plus charge. They are called as the cationic complexes. You can see the example here, hexamine chromium complex. Here, outside the square brackets, you can see the plus charge. In the similar way, diamine silver complex, you can see the positive charge. In the similarly, in this cobalt hexa aqua cobalt complex, you can see the plus 3 charge. So all the complexes which carry the positive charge are called as the cationic complexes. Now coming to the anionic complexes. In the anionic complexes, we are having the net positive charge of the complex as the negative charge. So you can see the hexacyanoferrocyanide complex, you can see -4 charge. In the similar way, here the cobalt hexafluorocobalt complex, you can see -3 charge. In the similar way, the tetracyano nickel complex, you can see -2 charge. So the minus charge is there for the complex. Such type of complexes are called anionic complexes. Now coming to the neutral complexes. Neutral complexes are the complexes which carry zero, they don't have any ion. These are not the ions. These are neutral compounds. If they have a charge, then you can call it as an anion. It might be cation or it might be anion. If it is neutral, they don't have the net charge is zero. Here you can see tetracarbonyl nickel complex. There is no charge over the complex. Similarly, pentacarbonyl iron complex. You could see no charge here. In the similar way, the complexes which do not have any charge on their square parenthesis, then such type of complexes are called as the neutral complexes. Now let me discuss, before explaining about the Sidgwick theory, I'm just giving you the important terms. So first let me see the coordination compounds or the complex compounds, the important terms involved in those complexes, in those compounds. The important terms are, the first one, you can see the central metal ion. The central metal ion is one which is in the center of the complex, and where the anion or the neutral molecules are attached by the coordinate covalent bond or the dative bond. It is given by the arrow mark. That is nothing but a central metal ion. The metal ion is in the center of the complex, and surrounding will be the anions or else the neutral molecules. They are called as the ligands. So ligand is an atom, the negatively charged species or the neutral charged species around the central metal ion. It is capable of donating a pair of electrons to the central metal atom. Such type of species, such type of molecules are called as the ligands. Now coming to the what is coordination number. The total number of ligands attached to the central atom or a central metal ion is nothing but the coordination number. Now let us see the diagram. How? Now what is a coordination sphere? The coordination sphere is nothing but, I have discussed the important terms, that is nothing but the central metal ion and the ligand. In the central metal ion and the ligand together as a whole, as a collectively, you call it as a coordination sphere. So here the coordination sphere is nothing but the central metal ion and the ligands attached collectively is called as a coordination sphere. So it is called as a coordination sphere. Now you can see, so previously I have explained about the central metal ion, I have explained about the coordination number, I have explained you about the ligands. So the important terms involved I have explained: central metal ion, ligand, coordination number, coordination sphere. So you can see the diagram over here. So you're having the square brackets. As I have told you, the coordination compounds are nothing but their formula is enclosed in the square brackets. Such type of compounds are nothing but the coordination compounds. So this whole is a coordination compound. It is enclosed, its formula is enclosed in the square brackets. This iron, it is nothing but the central metal atom. And this central metal atom, you are having cyanide. It can the cyanide anion, or you can take it's a ligand. Even the neutral species can be in this place of the ligand. A ligand can be the species, the negatively charged or the neutral species, which donates electrons to the metal atom. Central metal atom is called a ligand. Here the cyanide is the ligand. There are 6 ligands in this complex and only one central metal atom. So iron is the central metal atom. Cn ligand is nothing but the ligand, and the coordination number is the number of ligands. So cyanide are 6 in number. So the coordination number of the complex is nothing but the 6. So it is number of the ligands is called as the coordination number. So the cyanide is the ligand and it's in 6 number. So the coordination number is 6. Now, as a whole, the central metal atom and the ligand together, you call it as a coordination pair. It is nothing but the coordination pair. Now, the iron and the cyan are bonded with the dative bond, coordinate covalent bond. So these are the basic terms which you have to learn. So previous session, what I've explained is the theories of the coordination compounds. In that, we have explained about the Alfred Werner theory. And now I have explained the basic terms involved in the complex compounds. Now, let us go for the second theory. Now, let us go for the second theory. That is nothing but the Sidgwick theory. So before explaining the Sidgwick theory, you need to know what is an oxidation number. So how the oxidation number is calculated, we have to see. So I have explained you previously, this is the coordination pair. In this coordination pair, how you are getting the oxidation state for the central metal atom. So the charge present on the central metal atom is nothing but the oxidation number. The charge present on the central metal atom, electric charge present on the central metal atom, is nothing but the oxidation number or the oxidation state. Now, for instance, we take this complex, hexacyanoferrate complex will take. So this is nothing but the potassium ferrocyanide complex. This complex, it is an anionic complex with minus 4 charge. Here you take the central metal atom as a X, and each cyanide ion is having the charge of -1, and there are 6 cyanide ions. 6 into -1, it is equal to whatever is the charge you put on the LHS side, sorry, right hand side, RHS side. So here X plus 6 into -1 is equal to -4. So X minus 6 is equal to -4. X is equal to, once if the 6 goes to right hand side, you will be getting +6. So X is equal to 6 minus 4. X is equal to +2. So the oxidation state of the iron is +2. Now, in the similar way, we'll see here it is printed as capital O, but that is wrong. It is CO, small o, cobalt. CO, C capital O is a carbon monoxide. So it's a printing mistake. So C cap, this small o, it is nothing but cobalt complex. Tetramine chlorocobalt complex will take. So the ammonia, it is a neutral ligand. Its charge is 0. So let us calculate the oxidation state of the cobalt. Now this is X plus, here you're having 4 neutral ligands. Ammonia ligands are 4. 4 into each ammonia will give, it's nothing but 0 is a contribution. So its charge is, it gives 2 electrons. Each ligand will give 2 electrons. That is a secondary question. Now the charge of the ammonia is 0. So 4 into 0 plus, here the chloride ions are 2. 2 into each chloride ion has a charge of -1. Seventh group element -1 charge. It is equal to +1. The charge of this complex is +1. So it is equal to +1. So X, here 4 into 0 again 0. Again 2 into -1 is nothing but -2. X minus 2 is equal to +1. Once if this -2 goes to the RH side, you'll be RH side, you'll be getting X is equal to 2 plus 1. It's nothing but 3. The cobalt oxidation, capital C, small o, its oxidation state is +3. So we have seen the calculation of the oxidation state of the cobalt as +3. Now let us go for the platinum complex. So diamine dichloro platinum complex, will see what is the oxidation state of the central metal ion platinum. So let us take it as X. X plus 2 into 0. The ammonia is a neutral charged ligand. It donates the electrons, but its charge is 0. So charge is 0 and you're having two ligands. 2 into 0 plus here chloride ions are there. 2 Cl, each Cl gives 1 -1 charge. So 2 into -1 is equal to 0. So X minus 2 is equal to 0. So 2 into 0, 0, 2 into -1, -2. This X minus 2 is equal to 0. Why I am putting here 0? Because this is a neutral complex. It is not having any charge. Previously, I have seen a anionic complex. Here we have seen a cationic complex. Now I am explaining you for the neutral complex. So here the charge is 0. So X is equal to -2. Once it goes to the RHS side, X is equal to +2. So therefore, the oxidation state of the central metal ion, that is platinum, it is calculated as +2. So this way we calculate the oxidation states. So before explaining the Sidgwick theory, you need to know to calculate the oxidation states. So now coming to the what is a complex ion. I have explained you complex ion is nothing but a complex ion is it is electrolytically charged species, or sometimes it's a neutral one. So the types of complexes. Now previously I have explained you the types of complexes: cationic complex, anionic complex, neutral complex, and the important terms involved in the coordination compounds. The important terms that are involved in the coordination compounds are central metal atom, ligand, oxidation number, complex ion, coordination number. What is coordination pair? I have explained you. So now we know how to calculate the oxidation number. Now let us switch on to our second theory. That second theory, theories of the coordination compounds. In that Alfred Werner theory is completed and we have got so many concepts. And now let us go for our second theory. Basing on the first theory defects, we have got the second theory. That second theory is Sidgwick theory. So Sidgwick, he has given the theory. It is just the interpretation, electronic interpretation. Sidgwick theory, it is the electronic interpretation of the Werner theory. All the ligands are capable of coordinating with the metal. Every ligand means that should compulsory, it should 100% coordinate with the metal complex, or else that is not a ligand. Now the second one, this is the second postulate. And the third one, here the ligand donates. Here each ligand will donate a pair of electron to the central metal atom. Once if the ligand is present in the coordination sphere, it should 100% donate a pair of electrons. 2 electrons should be donated to the central metal atom. And then only it can form a coordinate covalent bond and it is able to coordinate with the metal. If it doesn't donate, it cannot coordinate with the metal in the central metal atom in the complex. So therefore, it cannot form the coordinate covalent bond. It cannot be the part of the sphere, coordination sphere. So every ligand should donate a pair of electrons. Now, this coordinate covalent bond is represented by the arrow, as previously I have told you. Here it is the arrow mark. So this arrow mark, just as an arrow mark, it does coordinate covalent bond. It is represented by the arrow. from ligand to the metal, where ligand is the donor of the electron pair and the central metal atom is the acceptor. So it is a central metal atom is the acceptor. So here it acts as the Lewis acid. The metal acts as the Lewis acid and the ligand acts as the Lewis base. So it donates a pair of electrons. This ligand acts as the Lewis base and the metal atom acts as the Lewis acid. It accepts the electrons. Now we can see the complex over here. In this complex, you're having the primary value. You could see the hexamine cobalt chloride complex, where you can notice the primary valency and the secondary valency. Similarly, as Werner has explained, even he is explaining the same primary valency and the secondary valency. Primary valency is nothing but the ionic bonds outside the sphere. Whatever ions are there, they are the ionic bonds and they easily get broken down. So the primary valency is nothing but the ionic bonds, and the ones which are within the sphere are the secondary valency. These are called as the coordinate covalent bonds. They are called as the coordinate covalent bonds. So once again, we recall all the ligands are capable of coordinating with the metals in the complex, and each ligand donates a pair of electrons to the central metal atom and thereby forming the coordinate covalent bond. The coordinate covalent bond, it is represented by the arrow mark. Here, this is the coordinate covalent bond. It is represented by the arrow mark. So this is a coordinate covalent bond. Each ligand, it forms the coordinate covalent bond. This is the donor. Ligands are the donors and the central metal atom is the acceptor. So this is a Lewis acid and this is a Lewis base. So the ligand, the coordinate covalent bond is represented by the arrow from ligand to metal atom, from the ligand to the metal, where ligand is the donor, it is the Lewis base, and the central metal atom is the acceptor, it is the Lewis acid. So here is an example we have explained. So how many coordinate covalent bonds are there? Dative bonds with the arrow marks. There are 6 coordinate covalent bonds. So this will contribute to the secondary valency. And outside the sphere, you are having the primary valency. They are the completely ionic bonds. These are the coordinate covalent bonds and these are ionic bonds. This is primary valency, and the ones which are forming the coordination sphere are the secondary valency. The coordinate covalent bonds present is nothing but the secondary valency. Now let us see, these are the postulates. Every ligand is capable, here you can see every ligand is capable of coordinating with the metal in the with the metal in the complex. Next, each ligand is donating a pair of electrons. So this is a donor, a Lewis base. This is the acceptor, a Lewis acid. So this 6 ligands are there. Coordination number is 6. Central metal ion. So these are contribute to the secondary valency. Outside the sphere will contribute to the primary valency. These are ionic in nature. So these are very strong bonds, coordinate covalent bonds. These contribute to the stability of the complex. Now let us see a very, very important concept, effective atomic number, which was explained by Sidgwick. So once if you remember EAN, whom do you remember? We remember Sidgwick, the scientist Sidgwick, EAN, Sidgwick. So once for the coordination compounds, a very, very important concept, effective atomic number. So what is effective atomic number? It is nothing but atomic number of the central atom minus the oxidation state of the central atom and the electrons gained by the metal from the ligands is the effective atomic number. So Effective atomic number. Once again, I'm giving you a very clear definition for this. Effective atomic number is defined as sum of the effective atomic number. It is the sum of the electrons of the central metal atom and the electrons donated by the ligand to the central metal atom. I'm repeating, the sum of the electrons of the central metal atom and the electrons donated by the ligand to the central metal atom is called EAN, effective atomic number. And if once that is equal to the nearest inert gas atomic number, then the complex is a stable complex. Once if you explain about the complex, you just get an idea of a stability. Once if you talk about a complex coordination compound, I just remember the stability. These are the highly stable compounds. Once, as previous session I've explained you, once if you put the solution, any solvent, you take a complex, you put in the solvent, the identity is not lost. So the stability is there for that sphere. It is just because of the coordinate covalent bond, and the coordinate covalent bond contributes to the EAN, effective atomic number. They will get the inert gas configuration. They'll be getting the atomic number of the nearest inert gas configuration. So they're highly stable just because of this EAN. So Sidgwick, a very important concept, has been explained by the Sidgwick. It's nothing but EAN. So he suggests metal ion continues to accept. So once a metal is there, it bonds with the ligands, it takes the electrons, it continuously accepts the electrons. So central metal atom is having the vacant orbitals. Ligand is having the electrons. So the ligand is donating the electrons and the metal is accepting the electrons. So it accepts the electron pairs till the total number of electrons in the metal donated by the ligand is equal to the nearest inert gas configuration. Until it gets the atomic number of the nearest inert gas configuration, you are having inert gases. Helium, neon, argon, krypton, xenon, you are having. So until it gets the atomic number to its nearest value. So until it gets the atomic number of the nearest inert gas, it keeps on accepting the electrons, and thereby it gets the stable configuration. It gets the stability after gaining these electrons. It keeps on accepting the electrons until it gets the stability, until it gets the atomic number of the nearest inert gas. So EAN is equal to Z minus OS plus 2N. So L is the monodentate ligands, or the number of electrons donated by the ligands. So the next Z, L is the number of ligands, Z is the atomic number. Okay, so next atomic number of the metal atom minus the oxidation state of the central metal atom. OS is nothing but oxidation state of the central metal atom. So L is the number of monodentate electrons, or the number of electrons donated by the ligands. So here, and you're having Z is nothing but the atomic number of the central metal atom. OS is the oxidation state. Now let us see the EAN calculation for some complexes. So I have picked the examples from the Telugu Academy. Let me explain you some of the examples. So potassium, you are having here hexacyano iron, potassium hexacyano iron complex, ferrite complex you take. Here the atomic Z I have explained you, Z is the atomic number. How much it is? 26. Previous slide I have explained you the oxidation state calculation. Oxidation state calculation I have explained you. Potassium, it is +1, 4 into +1 +4 plus X plus 6 into cyanide -1, 6 into -1, so -6. So +4 plus X minus 6. is equal to 0. Here you are having the neutral charge is equal to 0. So plus 4 plus x minus 6 is equal to 0. So you'll be getting x minus 2 is equal to 0. X is equal to plus 2. So what is the oxidation state of the iron? It is plus 2. Previously I have explained you calculation of oxidation state. Previous slide. So here the central metal ion oxidation state is plus 2. Atomic number is 26. So total number of ligands are 6. Now so EAN is equal to Z minus OS plus 2L. 26 minus 2 plus 2 into 6. Here is atomic number minus oxidation state. Here you are having the oxidation state 2 plus 2 into how many ligands? L is equal to 6. Here coordination number, ligand number, it is 6. 2 into 6. So 26 minus 2, 24 plus 2. So this is equal to 36. Now, similarly for the nickel tetracarbonyl complex, we'll see. Here, nickel atomic number is 28. The oxidation state, it is 0 each. Here, this is carbon monoxide, ligand. Okay, previously, capital C, small o is cobalt, capital C, capital O is carbon monoxide. So, carbon monoxide is a ligand, capital C, capital O. Capital C, small o is a cobalt. So for that is the cobalt central metal ion. Always that will be the central metal ion and this will be the ligand. So nickel tetracarbonyl complex will take here Z atomic number say of the central metal atom. Nickel central metal atom, it is 4. Nickel central metal atom, its atomic number 28. Now what is the oxidation state? Here each carbon monoxide ligand, it gives 0. So it's a neutral ligand. It's a neutral ligand. So 4 into 0 is nothing but 0. X plus 0. So X is equal to 0. Nickel oxidation state is 0. I have calculated the oxidation state. Now EAN is equal to Z minus OS plus 2L. So what is Z? Atomic number 28. What is the oxidation state? 0 plus 2L. What is L? L is the number of ligands. L is the number of ligands. So 2 into number of ligands are 4. What is 2? 2 is nothing but the pair of electrons donated by each ligand. So the formula I've told you, each ligand will donate a pair of electrons. So pair is nothing but 2. So 2 into 4. It is 36. So 28 minus 0, 28 plus 2 into 4, 8, 36. 36, it is the atomic number of krypton inert gas, the nearest inert gas. For the nickel, this is the nearest inert gas. Here for the iron, this is the nearest inert gas. Now let us go for the next complex. Here it is a typing mistake. It is cobalt. Capital C, small o. Capital C, capital O is nothing but carbon monoxide. Capital C, small o is nothing but the central metal atom, cobalt. So this here, it's capital O, it's a printing mistake. It should be small o. Capital C, small o, cobalt. You're having 6 ligands. Within the sphere, you're having 6. So the ligand within the sphere is only called the ligand. There are 6. Coordination number is 6. Okay, outside the sphere, it is not the ligand. They are ionic in nature. They don't donate the electrons. Only the ones which are within the sphere are the ligands. They donate pair of electrons. Okay, so now we'll calculate the EAN. Z is equal to 27. Cobalt atomic number is 27. Z is the atomic number of the central metal ion. Cobalt, it is 27. Now we'll calculate the oxidation state. Previously, how I've calculated, the similar way we'll calculate. Ammonia, it is the neutral ligand. 6 into 0, 0. X, this is X plus 6 into 0 is 0. So X is equal to, here, chloride. Each chloride will donate 3. So here we'll see each chloride minus 1 charge, 3 into minus 1. So X plus 6 into 0 minus plus 3 into minus 1. I'm explaining once again. X plus 6 into 0 plus 3 into minus 1 is equal to 0. X minus 3 is equal to 0. X is equal to plus 3. So the oxidation state is plus 3. Okay. The number of ligands are 6. Here, these are the ligands. While calculating the oxidation state, you have to take the total ones. Total. Central metal ion. Besides central metal ion, whatever are the species, you have to consider them. But within the sphere are only contributed to the ligands. Okay, EAN is equal to Z minus OS plus 2 into L. 2 is nothing but pair of electrons. Each ligand will give pair of electrons and 2 electrons. So EAN is equal to 27 minus oxidation state, that is 3, plus 2 into ligands. How many you are having? 6. Within the sphere only 6 ligands, ammonia ligands. So 24 plus 12. So 27 minus 3 is 24. 6 into 2, 12. 24 plus 12, it is 36. Nearest inert gas concentration, 27. Nearest one is 36. Krypton, oxidations, atomic number. So these are highly stable complex because here, as he has explained, they are gaining the central metal ion. It is accepting the electrons from the ligand until it gets the stable inert gas configuration. Central metal ion, how it is always accepting the electrons from the ligand. By accepting the ligands, it is able to form the coordinate covalent bond. Therefore, it is able to form the complex. So how many ligands will contribute? How many ligands will coordinate until it gets the stable configuration. So here 6 are coordinating. Here 4 are coordinating with the central atom. Here 6 are coordinating with the central atom. Thereby, it is getting the nearest inert gas configuration and they are getting stabilized. So the coordination compounds are getting stability with this EAN. Now, in the similar way, I'm going to show you one more some of the calculation picked from the Telugu Academy. Here, you can see the complexes. Hexacarbonyl chromium complex. Chromium atomic number 4. Number of electrons. Number of electrons lost in forming the metal ion. Oxidation state is 0. Here, this one column is nothing but the oxidation state. Here it is 0. And the number of electrons from the ligands, 6 into 2, 12. Okay, by calculating, you'll be getting 24 minus 0 plus 12. You'll be getting 36. Krypton configuration. Similarly for iron, even for iron, atomic number is 26. Oxidation state, as previously I've explained, on calculation you'll be getting plus 2. And the number of electrons from the ligand, 6 ligands, 6 into 2, 12. Okay, now using the formula EAN, 26 minus 2 plus 12, 36. Nearest inert gas configuration. In the similar way for the cobalt, atomic number is 27. In this complex cobalt, hexamine, cobalt complex, the central metal atom, it is 27. So oxidation state calculated, here it is 0. Okay, x plus 6 into 0, 0 is equal to plus 3, x is equal to plus 3. Here it's the oxidation state is plus 3. Okay, so number of ligands 6, 6 into 2, 12. So electrons from the ligands are 12. So 27 minus 3 plus 12 is equal to 36. It is equal to nearest inert gas configuration, that is krypton. Now, similarly, nickel tetracarbonate, previously I have explained this example, you are getting 37. Similarly, tetracyanocopper anion complex, you'll be getting here 36. So 29 is the atomic number, plus 1 is the oxidation state. Okay, how you're getting plus 1? See, 4 into minus 1, minus 4, x minus 4. Okay, is equal to minus 3. So again, once if you see, that goes to the RHS side, x is equal to 4 minus 3, plus 4 minus 3, it is nothing but 1. The copper, it is getting the oxidation state plus 1. So 4 into 2, 8 electrons. Ligand, electrons donated by the ligand. So you'll be getting 36. 29 minus 1 plus 8. Similarly, palladium, hexamine palladium cation also you'll be getting. Okay, so 46 atomic number, 4 is the oxidation state, 12 are the electrons donated by the ligands. You'll be getting the xenon oxidation state nearest inner gas configuration. So that is 54, it is stabilized complex. Similarly, for the platinum, hexachloroplatinum. Okay, so these are the examples for EAN, a very, very important concept. So, which was explained by Sidgwick. So, now we'll see the limitations. So much he has explained an important concept he has given. As I've told you in the previous session, everywhere there are some drawbacks, limitations for every theory. So basing on the limitations, you are getting the new theories. So here the limitations are, here he's not able to explain some of the compounds doesn't obey EAN rule, but how they're getting stabilized was not explained. Most of the compounds are following EAN rule, but the complexes, some of them they're not following EAN rule, but still they're stable. That couldn't be explained by Sidgwick. And sometimes the electrons pair that are getting donated by the ligand to the central metal ion. So there is an improbable charge, negative charge on the complex. So how he couldn't explain. And the magnetic properties as well as the color properties are also not explained. Similarly, even the geometrical shapes for the complexes like octahedral complex, tetrahedral complex, square planar complexes, how the ligands are approaching, how it is forming, what is the shape of the complexes were not explained. Magnetic properties, as I've told you, diamagnetic substances, paramagnetic substances, ferromagnetic substances. So such type of magnetism is not explained. And the color of most of the complexes exhibit the color, but why was not explained by the Sidgwick theory. He has just explained, mostly he has explained the EAN concept. So so only few postulates were given by his theory, and along with that EAN was explained by Sidgwick. That is nothing but the electronic interpretation of the coordination compounds of the Vernier theory was explained. That's it. But he couldn't give in detail about the remaining properties. That were the limitations for this theory. So, but still we can be very happy with the EAN concept, a very, very important concept for the coordination compounds. Okay, I hope everybody have understood. So we have started about the coordination compounds, theories of the coordination compounds. So I have explained the previous session, the Alfred Werner theory. So actually inorganic compounds, how they are different types. So salts, anion, cations, salts, addition compounds. In these addition compounds, double salts you'll be getting. Double salts lose their properties in mixing with the solvents, but even on the evaporation and mixing with the solvents, the ones which doesn't lose their property and get extra properties are nothing but the coordination compounds and the complex compounds I've told you. So these coordination compounds, now we are seeing theories of the coordination compounds, bonding of the coordination compounds. These bonding of the coordination compounds, you are having 5 theories. In these 5 theories, the first one is the Alfred Werner theory, which I've given you, and the limitations were given. Now the Sidgwick theory. So next class we'll see the valence bond theory. thereby we'll see the crystal field theory, ligand theory, and you'll be getting the molecular orbital theory. Okay, for our UG session. So Werner theory, valence bond theory, and crystal field theories. Okay, I hope everybody have understood my session, and if any doubts, you can put in the you can ask me later on. I'll be giving you the contact number. Okay, students, thank you.